Okay. So, how you doing? What was that homework?
Good.
Long?
Oh, I got half of it at least. I'm telling you, you're done. You're done.
Well, the exam's gonna be very similar to the homework.
Which part?
Shorter, because you only have 2 days. I will give it to you at the end of the lecture today. I wanted to cover a couple more things that might be useful for that exam. Make sure that we answer all questions that you may possibly have. Exam is due on Thursday. There's no class on Thursday, so you can take the class time to complete it. And then put it under my door, my mailbox. In order to put it on my mailbox, you cannot, technically students cannot walk into the mailroom, so you have to give it to the secretary or somebody there, and then they can put it on my mailbox. That's an option. So we'll talk about that in a minute. So let's see. So we had finished our discussion of the Bessel equation of order nu, and that's something that's going to be relevant for the exam. There's one question whose answer to tell you that right now is Bessel functions. So this is the last lecture of section number 2, number 17. So after this lecture, after Thursday, you turn in your exam. On next Tuesday, we'll start the topic of eigenvalue problems and partial differential equations for the purpose of solving initial value problems and boundary value problems. We'll do some analytical solutions and some numerical solutions as well. So we had talked about the Bessel equation of order nu, and that equation looks, again, remember, like this: x squared d second y dx squared plus x dy dx plus m squared x squared minus nu squared y of x is equal to 0. Okay, and we said also that it wasn't arbitrary that we picked an equation that looks like this. The reason why we picked this equation is because it shows up all the time. It will show up on heat transfer problems and fin equations in 1D. It will show up in partial differential equations when you separate the radial coordinate. That's what you will get for the radial direction in a separable partial differential equation. So that equation shows up all the time. So obviously somebody had to come in and find a general way of solving this equation. And this was done through Frobenius method. So the solution is in terms of some infinite series. And it turns out that those infinite series were later given a name. And those names are basically the Bessel functions. J of the first kind of order nu plus C2 J minus nu mx. That is, if nu is not an integer. If nu is an integer, then we have C1 times J nu of mx plus C2 times Y nu of mx. That is, if nu is equal to an integer. And this is the classical solution for the Bessel equation of order nu. Okay, and we showed what those functions look like, or the evaluation of those nasty looking infinite series, which are actually not infinite because we have that factorial and factorial square in the denominator, so those terms actually decay very fast, so we can easily truncate the series and find a very accurate solution. So those equations, those solutions look like this. This is the Bessel function of the first kind of order nu, and this is the Bessel function of the second kind of order nu. Okay? The Bessel function of the second kind is singular at x equals 0. It goes from minus infinity, and they both oscillate infinite number of times, but unlike the sines and the cosines, those oscillations are not periodic, okay? The roots actually contract as they progress towards in the x direction. Okay, another equation that you would find and that would arise in many, many applications in engineering, mostly heat transfer again, is the modified Bessel function or Bessel equation of order nu. And that equation looks like very similar to the one before. Plus x dy dx, but instead of having a plus, we have a minus here. And then this is a plus. So the new term is still negative. But now the x squared term that multiplies y is negative as well. So the only difference between that equation and the equation above is that term being negative, this one's being positive. Now, that term being negative makes the solution completely different, radically different to this one, in terms of what the solution looks like. The fact that these is a plus sign leads the solution to be oscillative. Okay? Sort of what you would end up with an equation. Remember the equation where you don't have the x squared here, you don't have this term, and all you have is d squared y x squared plus yx equal to 0. That solution is sines and cosines, right? But if you had the minus sign, you have exponentials. So the plus sign makes it oscillate because the roots are imaginary, right? And the minus sign makes it decay. So if you didn't have the variable coefficients, you will then have cosines and sines for these one, and you will have exponentials or cosine hyperbolics for these ones, right? So there's an analogy, obviously, associated with these sign, but it's in terms of other kinds of Bessel functions. So the trick here is to let z be equal to ix. So to turn this equation into an, you can actually play this trick using the standard cosine sine equation, and you will end up with the exponential solution as well. So if you do a variable transformation from x to z, where z is a complex variable, notice that z squared is equal to minus x squared, and then you can use it to transform the differential of x in terms of differential of z, and so on and so forth. Then the equation that you would end up with, this leads to z squared, the second y dz squared, plus z dy dz, plus m squared z squared minus nu squared y of z is equal to 0. So making that substitution would lead to that equation, and obviously, as you can see, that equation looks just like this one. But now it's in terms of z, and then instead of being in terms of x. Well, obviously, you can see that the solution to this equation is C1 j nu mz plus C2 j minus nu mz, or C1 j nu mz plus C2 y nu mz. This is if nu is not an integer, and this one is nu is an integer. All right, so now we have a solution in the complex domain, and all we need to do is transform it back to the real domain. So therefore, because z is equal to ix, then the solution in terms of x is simply c1 j nu of imx plus c2 j minus nu imx, or c1 j nu imx plus c2 y nu imx. Again, this is, why am I using m? Yeah, this is m. Why am I this is if nu is not an integer, and this is if nu is an integer. All right? So if we go back to the definition of the Bessel function, remember the Bessel function nu of I m x is then equal to the summation from n equals 0 to infinity of minus 1 to the power of n times I to the power of 2n plus nu mx divided by 2 to n plus nu divided by n factorial times the gamma function of n plus nu plus 1. That was the definition of the Bessel function of order nu. All we just added was the I, and you just took it out. It would be inside this parenthesis, we just separated it into its own. Right? So furthermore, J nu of I m x is equal to then I to the nu, the summation from n equals 0 to infinity. So remember, I squared is equal to minus 1, I to the 4th is equal to 1, I to the 6th is equal to minus 1, I to the 8th is equal to, you know how the sequence goes, right? I squared is minus 1. If you square that, you get 1. I to the 6th is, so basically this I to the 2n times I to the nu, we can take I to the 2n, and that's minus 1 to the power of n. So those two can actually cancel out. And all we're left with is I to the nu. And this is just simply 2n plus nu, n factorial. And that function, or that particular infinite series, we call I of nu mx. Same thing. So this one receives a name, and we call that one I, such that I nu is the modified Bessel function of the first kind of order Alright, so when we stick an I in the argument of a Bessel function, we get a modified Bessel function. Sort of what happens when we stick an I in the argument of a cosine, we get an exponential. Remember that? We remember Euler's expressions? When we stick an I in the argument of a cosine, the cosine of Ix is basically an exponential function. Same thing happens here. When we stick an I in the argument of a Bessel function, we get a modified Bessel function. This one is one that oscillates. We expect this one to be one that doesn't oscillate. And vice versa. We stick an I in the argument of a modified Bessel function, we get back the regular Bessel function. And similarly, y nu of I mx has a name, and we call that k nu of mx. This is an x, not a k. Such that k nu is the modified Bessel function of the first kind, second kind of order nu. This is analogous to Euler's formula. That e to the I theta is equal to cosine of theta plus I sine of theta. So when we stick an I in the argument of an exponential function, we get trigonometric functions, and vice versa. When we stick an I in the argument of a trigonometric function, we get exponential functions. And these functions look like this. They're always positive. This is x. And they're not oscillative. I0 grows like this and intersects here in 1, and then the other ones grow like this, and so on. I1, I2, and so on and so forth. You can see they don't oscillate, they don't have infinite roots like the regular Bessel functions. And this is something that is going to play a major role on our next sections, okay, when we try to solve partial differential equations. And the k's are singular, and they go like this. So this will be k0 of x, k1 of x, and k2 of x. So remember, second kind are always singular, x equals 0. First kind are non-singular. The regular Bessel functions oscillate, the modified Bessel functions do not oscillate. So if we're solving a heat transfer problem, let's say on a fin, we can expect the solution to be in terms of these ones, not the oscillative ones, because heat transfer problems are diffusive type of problems, they don't oscillate. If we're solving a wave-like problem, we can expect the solution to oscillate. So if it's a wave-like problem with variable coefficients, we can expect the solution to be in terms of regular Bessel functions and not modified Bessel functions, because it's a diffusive type. Okay? For example, if we're solving heat transfer in a triangular fin, remember when you took heat transfer, what were fins for? Fins are just basically a way of increasing the surface area so that we can increase heat transfer through conduction and convection. So if we have a wall here, and let's say we have a hot element here and we want to remove more heat out of that hot element, we can do so by putting a fin. In this case, we're going to try a triangular fin. Okay? So basically, if we look at this in 3D, we're going to have, this fin is going to have convection on this by convection coefficient H, surface area A, T minus T infinity. That's Newton's cooling law, where T infinity is the temperature of the fluid. And if we apply a control volume analysis, let's say that this is our control volume. So assuming that this is control volume, and this is a convective area, I'm going to call it AC. This is the area of the periphery of those surfaces, of flat surfaces. So the control volume looks sort of like this. And when we have Q through conduction going at x, this is of size dx. We have Q of conduction going at x plus dx. And then we have, on this wall, we have convective Q going on the periphery. So Q from conduction at x is equal to minus K. This area of conduction, we're going to call this the area of the periphery. I'm sorry, not AC, that might be misleading. It's not the conductive area, it's the convective area, which is the periphery there. So it's KAC times dt dx. Well, the conductive heat flux that comes out at x plus dx would be QC at x plus dQC dx at x dx. This is a Taylor series expansion. And Q convection at the periphery is equal to H, area of the periphery, which is equal to H P dx, which is the perimeter, T minus T infinity, and this is the perimeter. Okay. So this is how we formulate the equation, and then conservation of energy basically says whatever goes in minus whatever goes out plus whatever is generated is equal to the partial with respect to time of whatever is inside the control volume. Let's assume that there's no heat generation, and let's assume that this is steady state. We're interested in the steady state response of this problem. And generation meaning that whatever material this fin is made of there might be some kind of chemical reaction inside that has internal heat generation. We're assuming that that's zero. It's just a passive metal that we're using as it is used in all cases of fins. So basically, in is Q by conduction at x, out would be Q by conduction at x plus dx, plus Q by convection at the periphery. And that's equal to 0. And at the end, the equilibrium equation would be, if we plug in all these values up there, will be d dx of k, the cross-section area to which conduction takes place, dt dx, minus h p, that's the perimeter, t minus t infinity, is equal to 0. Such that let me frame this one, triangular fins, the cross-section area as a function of x, notice that the cross-section area changes, and we're just going to do a little drawing here, is L times delta divided by B times x, while the perimeter as a function of x is equal to 2L plus 2 delta over B times x. So let me do a little schematics here of what these quantities are. So if I go like this is a triangular fin. Let's say that this is the fin tip, and we're going to define the x-axis in this direction. This is B, and this is 0. So the x-axis goes to the left. 0 is the tip of the fin. B is the total base, or the length of the fin. This distance from here to here, we call delta. That's the height of the fin. Well, say that this is the width. distance from here to here, is L. And the perimeter, remember, is the sum of these four sides. That's the perimeter. So as you can see, that's why the perimeter is 2 times L plus 2 times this height, which is a function of x. So we end up with an equation the resulting equation is x the second phi, or sorry, theta, the x squared plus d theta, the x minus gamma squared, d of x, or theta of x is equal to 0. Such that theta of x is equal to t of x, this is what we're trying to solve for, the temperature as a function of x, minus d infinity. So it's just a shifted temperature. And gamma is equal to the square root of twice h b over k, that's the conductivity, divided by delta, which is the height of the fin. All right, so that doesn't look like it is a second order differential equation with variable coefficient. There's an x right here, but it doesn't look like the Bessel equation or the modified Bessel equation or the Euler-Cauchy equation. Remember the Euler-Cauchy equation? We had x squared, x, and nothing. Okay, just a constant. The Bessel equation we had x squared, x, x squared. Right? The modified Bessel equation we had x squared, x minus x squared. Okay, this looks more like the modified Bessel equation because of the minus sign here, but the coefficients do not match. So there's a trick that if you let x be equals to xi squared, you're going to do a variable transformation, then the equation in terms of xi would look like this: xi squared, the second theta of xi, the xi squared, plus xi times d theta of xi, d xi, minus 4 gamma squared, xi squared, theta of xi is equal to 0. And that, as you can see, is the modified Bessel equation. So after a few tricks, we got there. And the answer to that, well, we know what the solution is of the modified Bessel equation. So, therefore, the solution, and I'm going to write the solution in terms of x, which is dx minus d infinity, is equal to A, constant of integration, Bessel, modified Bessel function of the first kind of order 0, 2 gamma times square root of x. Okay, because the solution is in terms of psi, but psi is the square root of x. See, the solution to this equation is in terms of I0 and K0 of psi, but psi is the square root of x. That's why we end up with the square root of x plus b, K0, 2 gamma, square root of x. And that's the final answer of that equation. All right. Now, we got constants of integration there, A and B. What do we do with those constants of integration? Or what do we need to be able to determine those constants of integration? This is a general solution. This is a general solution to the triangular fin problem. So if you have a triangular fin, the temperature distribution and hence the amount of heat that you can remove, because the amount of heat that you remove because of the fin is proportional to dt dx, right? Heat conduction, k dt dx. So if you have a triangular fin, the solution is in terms of Bessel functions, modified Bessel functions of square root of x. And this gamma contains convection and conduction and size and so on, all that information. We put gamma right here. It contains convection coefficient, contains the base of the fin, it contains the conductivity, it contains the height of the fin. So geometric convection and conduction information is all embedded into gamma. So a simple problem such as heat conduction in a fin like that in a triangular section is the solution is in terms of Bessel functions. But in order to fix A and B, what do we need? Boundary conditions, right? General solution plus boundary conditions gives you a particular solution. All right. So solutions are usually, boundary conditions are usually need boundary conditions. And x equals 0 and x equal b. Those are the boundaries of this problem. X equals 0 and x equal b. Normally we know what's going on at b. We know what goes on at B. Well, that fin might be trying to remove heat from a chamber that is very hot. So we might know the temperature there. Right? For example, from an internal combustion engine cylinder. Right? So we have a cylinder. Normally, in an internal combustion engine cylinder, the fins are cylindrical, or what do you call them? They're disc type of fins, okay, that go around the cylinder. But there might be a triangular fin trying to remove heat from this chamber on the left-hand side. So we might know the temperature at B. So we may know, such as temperature at B is equal to some TB. What do we know at x equals 0, at the tip? Normally we don't know anything. Right? There's nothing we can say. We don't know what the temperature is going to be. If this temperature is 500 degrees, we know that the temperature is going to decay because of the convection, right? We know we have convection up here. We know that T infinity might be, the flow temperature around here might be, I don't know, 50 or 40 degrees, whatever it is, and at whatever rate is removing energy, H. But we know that the temperature is going to decay from 500 or whatever it is over here to something, but we don't know what it is. There's tricks that we can play at the tip. We can say that the temperature, because the area of the tip is infinitesimal, it's very small, we can say that the conduction on the tip is 0. So we can say that the TDN or the TDX at the tip is 0. But there's something else that we can say that will remove one of those constants immediately. What do you think? This is going to be relevant to the exam, so I'm going to let you think about this. something happens at the tip that is going to allow us to get rid of one of those constants immediately. Think of the nature of I and K. What is K? At x equals 0. What do we call this? Singular, right? It's infinity. So K is a singular function at x equals 0. Can the temperature be singular? Can the temperature be infinity? No. So the only way for the solution to be possible is if B is what? 0. So at t equals 0 is equal to finite. That would make B 0 automatically. We cannot afford to have K in this solution because otherwise that will lead to a singular temperature, and that's impossible. All right. And then the other constant A you fix with whatever this is. That's it. So one more thing. Before I show you the exam and we discuss it, there's another form of the Bessel equation which is called we looked at the Bessel equation of order nu, we looked at the modified Bessel equation of order nu, and now we can look at what we call the generalized Bessel function, or Bessel equation. The generalized Bessel equation looks like this: x squared d second y dx squared plus ax dy x plus b squared x squared y of x is equal to 0. And I'm just going to jump this to the solution as solutions y of x is equal to c1 x to the nu j nu of bx plus c2 x to the nu j minus nu of bx. That is, if nu is not an integer, or c1 x to the nu j nu bx plus c2 x to the nu y nu bx if nu is an integer, where nu is equal to 1 minus a divided by 2. And that's a product of a couple of variable transformations I'm not going to go through. Basically, you can make x equal to xi to the power of something, and so on and so forth, and then you end up with these. That's the answer. Similarly, the following equation arises in fin applications of different cross-section functions. Okay, that might be, instead of being triangular, it might be exponential, or any kind of shape of the cross-section of the fin. That equation would look like this: d dx of x to the alpha dy dx plus gamma squared x to the beta y of x is equal to 0. Again, this is second order variable coefficient, ODE. Let me show you what the solution looks like. Right? So y of x as a case 1. That is, in the case that beta minus alpha plus 2 is different than 0. And also alpha is greater or equal than 0 and beta, beta is greater or equal than 0. So alpha and beta are positive numbers. Beta minus alpha plus 2 is different than 0. That will lead to a solution and y of x is equal to C1 x to the nu divided by mu, j nu mu gamma x to the 1 over mu plus C2 x nu over mu j to the minus gamma or minus nu mu gamma x 1 over mu. That is, if nu is not an integer. And the other one plus C2 x mu if nu is equal to an integer. Such that mu is equal to 2 over beta minus alpha plus 2 and nu is equal to minus mu alpha minus 1 divided by 2. So if gamma squared is negative, is less than 0, that means that gamma is imaginary. So I will have a negative sign here. This equation will have a negative sign. Then you can replace j nu will become I nu, will become the modified Bessel function, and y nu will become k nu. Okay? And finally, the last case, if we have that equation and beta minus alpha plus 2 is equal to 0, that means that beta is equal to alpha minus 2. That's a special case, because notice that mu becomes infinity, so this equation is, the solution is not valid anymore. Then, I'll write the answer. Then the auxiliary equation will lead to different roots for m, m1, 2, and depending on m1 and 2, then we have if m1 is different than m2, y of x is equal to c1 x to the m1 plus c2 x to the m2. If m1 is equal to m2, which is equal to m, then the solution y of x is equal to c1 of x to the m plus c2 x to the m log of x. And if m is equal to mu plus minus I beta, then y of x is equal to c1 times x to the mu times beta cosine of the log of x plus c2 x to the mu times beta sine of the log of x. And this are the solutions of the Euler-Cauchy equation. Notice that this is Euler-Cauchy equation. And so all right, so these are the all possible scenarios where an equation can lead to solutions in terms of Bessel function, except on this specific case when those coefficients happen to be like that. But you can end up with solutions in terms of Bessel functions of first and second kind, or modified Bessel functions of first and second kind. These equation in particular, right here, I'm sorry. This equation in particular is very common on fin applications. So if you work in heat transfer and the automotive industry, equations of fin for removal of heat happens to work out and or happens to arise in that particular fashion or in that particular form. And the problem what the engineers work on is that the optimization of the solution, the optimization of the amount of heat transfer that you can remove from a section. And optimizing the heat transfer will be, well, kind of inversely solve this equation by maximizing the amount of heat that you want to achieve. And that would lead to the optimal coefficients alpha and beta that you would need on this equation so that the heat is maximized. And the alpha and beta are in terms related to the cross-section area decay of the fin. So by optimizing this equation, you might end up with a fin that looks completely different from what you had imagined. Okay? Well, the first attempt is do it triangular. Triangular fin is a specific form of this equation, which will lead to a solution in terms of K0 and I0. All right. Any questions? A lot of Bessel functions, but trust me, we won't have to worry about the infinite series. We'll treat the Bessel functions as if they were well-known functions like sines and cosines. Okay? Sines and cosines are also infinite series. They just happen to receive a name, sine and cosine. They're already pre-programmed in most mathematical spreadsheets. You go to MathCAD or MATLAB, you say evaluate the Bessel function of the first kind of order 0 at this particular value of x, it will give it to you because it's already pre-programmed. Okay, so we don't have to worry about evaluating an infinite series and truncating the terms because the denominator is huge and so on and so forth. These are already well-known functions, and they're well-known for a reason. As I said, these equations, the way these equations look, is not arbitrary. Okay, They look that way because they come about, they arise when we're trying to solve problems that are very common in science and engineering. And heat transfer, as you can see, this is what happens. And even the simple problems of trying to solve or separate partial differential equations in radial or cylindrical coordinate systems, which are obviously of main use and importance to us engineers because we do a lot of things in cylinders, pipes. So when you try to separate the solution of an equation, as we'll see in the next section of the semester, in a cylindrical coordinate system, the radial direction will end up being a Bessel equation of different orders, different kinds. Okay? So the solution in the radial direction of a constant coefficient and linear and homogeneous problem in cylindrical coordinate system is in terms of Bessel and Bessel functions. All right, so these Bessel functions are not useless. You were thinking that, okay, this is a Bessel function, when am I going to see this? You might not, but understanding them is of main importance because you understand the nature of why things happen in heat conduction or heat convection the way they do. And they also happen in fluid mechanics. There's special instances when in fluid mechanics the solutions in terms of Bessel functions. We use numerical techniques to avoid to have to expand solutions in terms of infinite series and end up with analytical functions that are difficult to evaluate like this. So we use finite elements and finite volumes and finite differencing to approximate the solutions, and we just end up with discrete representations of the answer. But if we don't understand where the nature of the actual solution comes from, we will never understand why a numerical approximation might not be accurate or how to interpret one. Then it becomes the job of a technician to use CATIA, right, and not the job of an engineer. All right? So, all right. Let's talk about the exam. Because these things that we're talking about here are relevant to exam 2. In exam 2, let's talk about exam number 2 here. Is take home, due Thursday, 10/29 at midnight. So anytime before midnight that you can get that exam to me or to my office, if you timestamp it, I'm going to trust you put the right stamp. I'm going to be here. I'm going to send somebody to get my exams Friday morning. So all of the exams need to be there or somewhere in the office. It obviously is open books and notes. The solution of the assignments will be posted. I already posted them, but they will be released at 6 p.m. today. So you can use those as well. The only thing I ask you is as individual, both the solution and the end up. So basically, you have to turn in your own exam, but you also have to work on your own exam. You can use computers, and you obviously need to use computers for one of the problems, two of the problems. And it's on ODEs. First kind, or first order ODEs, linear and nonlinear. Second order ODEs, constant coefficient and variable coefficients. Okay? So, let me show you what the exam looks like. Mm-hmm.
Can we email you the exam by 12? Or?
Yeah, you can email me the exam by 12. You scan the whole thing in a single PDF. Don't send me pictures, please. Just make a single PDF, send it to me, email it to me by midnight. But then bring the hard copy and bring it to me next week. Okay? On Monday if you see me, or Tuesday next class, bring me the hard copy. Okay? All right. So the exam has 5 problems. First problem is the solution of that first order ODE. It's obviously a nonlinear ODE. It's not separable. So you need to do it through an integrating factor. It becomes pretty straightforward. Okay? Okay, and then apply that initial condition to get to the analytical particular solution. All right. Are there any questions on this one? This one's straightforward. Then you're going to use Hoynes method. You can use the MathCAD spreadsheets that I gave you, or you can use your own MATLAB or Mathematica or whatever you want to use. But you use Hoynes method to approximate the solution of these equations, where f is equal to y squared plus t over y.
Does it matter on the graph if we show the other?
Huh?
Does it matter on the graph if we show the other methods as well?
Uh,
Or do you,
just remove them.
Okay.
You can just delete from
Just
the graph. Delete you mean the Euler and the
Yeah.
Runge-Kutta, just delete the other ones.
Okay.
Okay? You can leave the spreadsheet the same, but on the plot, just remove the other ones, because then it's confusing for me to see. And then you do the residual too. So I'm asking you to calculate the residual of the approximation. But just the residual of the Hoynes approximation. Okay? And you have to do this with n equal 10, n equal 100, n equal 1,000 time steps to a final time of 5 seconds. Okay? And we did something very similar on the homework. Problem number 3 will be solving the system of first order ODEs. But you do this numerically, okay? This one cannot be solved analytically. It's variable coefficients, as you can see, t squared, e to the minus t, is non-homogeneous. So the only choice we have for this one is analytic, it's numerical. So you use the spreadsheet that I gave you for systems of equations, okay? Systems of ODEs. In this case, k is equal to 3, as you can see. And these are the initial conditions, 1, 0, and minus 1. You're going to use the Runge-Kutta method with n equal 20, n equal 200, and n equal 2000 to a final time of 2 seconds. You're going to show the 3 approximations on the same plot, y1, y2, and y3. So you're going to give me 3 plots, where y1, y2, and y3 for n equal 20. Then y1, y2, and y3 for n equal 200, y1, y2, and y3 for n equal 2000. So 3 plots. There's no exact solution to compare it with, and therefore there is no residual. Okay? Questions? All right. The 4th problem is heat conduction on a fin. But this fin is a rod. It's a constant cross-section fin, and I'm giving you the equation right away. You don't have to derive the equation or anything like that. Okay? That equation looks like that. It just happens that this fin, the conductivity, is a function of space. So this is a functionally graded material with high conductivity at the base. Low conductivity at the base and high conductivity at the tip. And also this is, the film coefficient is also a function of x, which happens to be also low conductivity at the base, high conductivity at the tip. It might be that the fluid that is circulating around this fin is actually at high speeds at the tip and at low speeds at the base. All right? So basically, h is a linear function of x, beta x, and k is a linear function of x, alpha x. You plug those 2 in there, and you'll get an equation that looks like something like what we did today. Okay? It's going to be in terms of Bessel function. What happens when you have the negative sign? You get the other kinds of Bessel functions, right? The ones that do not oscillate. And then you get the t, and find the particular solution if we know that the t at L, at the tip here, is equal to TL. We don't know what's happening at x equals 0, but we don't need to. And then you plot the temperature distribution using these parameters. Okay? Get a general answer. Don't plug any numbers, and for part C, then plug in the numbers and see what happens to t as a function of x. No, it's analytic. Yeah. All right. And problem number 5. Any questions on that one? And problem number 5 is going to be about using or doing a series expansion. So you're going to use the Taylor series method to try to get an answer for this equation. This is called the Hermite equation, which appears in mathematical physics and statistics and many applications. Okay? And you get the solution using Taylor series, and remember you have to shift the indices, find the recurrence relationship, all of that. Find the two independent solutions. So if lambda is a non-negative integer, m, we replace lambda with m, and m happens to be an integer, positive integer, these are called the Hermite polynomials because of series truncate. They terminate automatically. Okay? And you're going to show me the Hermite polynomials of order 0, order 1, order 2, and order 3. Okay, by the way, if you Google Hermite polynomials, you'll see them. You see what they look like. Okay? But I just want you to give me the answer, show me the process of getting to the answer through Taylor series, show me why the series truncate or terminate when m is an integer, and then you can copy whatever you find on Google, on Wikipedia. The Hermite polynomials all over the place. And then you're going to show that the Hermite polynomials are orthogonal with respect to a weight function of e to the minus x squared. That means that a Hermite polynomial over m, Hermite polynomial over n, times that weight function e to the minus x squared, integrated from minus infinity to infinity, gives you 0 if m is different than n. Okay, and that happens to be, once you know what the Hermite polynomials are, which I already told you, you can get them from Google, from Wikipedia. So you can get Hermite polynomial of order 0 and Hermite polynomial of order 1, plug them in here, and try to integrate that, you get 0. Okay, it's pretty straightforward. So you basically don't need to solve part A and B to answer part C, because the Hermite polynomials are available everywhere. All you have to do is, and polynomial n0 is going to be a constant, and polynomial n1 is going to be a linear function. Okay, so how do you multiply a linear, how do you integrate a linear function times an exponential function? You have to do integration by parts, and so on. Okay, and that's it. Any questions? All right. So let me distribute these. And I printed these on double-sided, so make sure you check that you have all the pages. It should be 5. All right. If you have any questions, are we missing? No, we're not missing anything. All right. Turn that off.